Good morning, everyone. Today we are going to solve our entrance examination paper of numerical analysis and design. So here we go for the first question. It says, consider the equation fx equals to x squared minus 3x minus 1 equals to 0, where p equals to 1, comma 2, 3, 4, etc. Take p of your choice and use any one of the following method below and for selected method, right, these options. So we're gonna solve the first question here. So here for question first, function is given here. We need to find the roots of quadratic equation. We get to pick the value of p. Let's choose p equals to 2 to make the math easy. The given give this result fx equals to x squared minus 2x minus equals to 3. We will use the Newton Raphson method because it is one of the fastest and most popular iterative methods. Firstly, we will write the algorithm. So, algorithm it goes like firstly, we will take input the initial guess, tolerable error, and maximum iterations taken. Now, processing, we will define function of x and its derivative FSH. Start the loop from I to n, 1 to n and calculate x1 equals to x0 minus f x0 by f dash x0. If x1 minus x0 is less than e, output x1 as the root and stop. Otherwise, set x0 equals to x1 and repeat. Output the approximate value. Now we will go to the program. Here, firstly, we will define the function f with the argument given x and return the value calculated by function. And we will define another function df with argument x. Here, it will return the value calculated by differentiation of function. Now we will define the third function, which is in Newton-Raphson, which is that takes x0, e, and n as arguments and start the for loop. For I in range 1 to 1 n plus 1, we will take input fx0 equals to f. Here we call the function, here also we call the function. Now, if d or f, d of f x0 is equals to 0, then the derivative is 0 and method fails and return. If otherwise, x1 equals to x0 minus fx0 divided by dfx0, which was the Newton-Raphson main formula. Now we will print the iteration, which iteration is this, and value of x, which we have calculated here. Now, if the mod h of x1 minus x0 is less than our e, which is tolerance error, then we will print root founded and print the value of x1 and return. Otherwise, we will change the value of x0 to x1 and repeat the math and follow the Newton-Raphson method again. Return and x0 equals to x1. Now we will, as a main function, we will call the value. Now for test run for iteration for x0 equals to 2, x square minus 2x minus 1 derivative f dash x 2x minus 2. Now for iteration 1, x1 equals to 2 and x1 equals to 2 minus, and this is a fx upon fx. So we will get x1 equals to 2.5. Now for x2, we will change the value and calculate by same formula. So we will get another value which is 2.41667. Now go to the third iteration and calculate the x3. So here we get 2.41421. If we minus this from this, so we will get the error which is less than our tolerance error. It means it's converging and it's our solution. So we'll return this number. Now its complexity and geometrical interpretation says about its time complexity varies but converges quadratically 0 log n, and space complexity is 0 1. Only stores few variables. And geometric interpretation, we pick a point on the curve and draw a tangent line. See where that tangent hits the x-axis, and the new x-axis point become our next guess. Now, our interpolation for data points at F9. It's our second question. We will see what was the question saying. Here, it is the second question. Here it says, consider the data points, this is this, and evaluate F9 with any one of the following methods, Lagrange or neutral interpolation. And do the same algorithm program, evaluation, complexity, and geometrical analysis. So now we will perform our second question here. Here we are given data points where the x values are irregularly spaced. You can see that because the spacing is not uniform, we will use Lagrange interpolation. It's highly reliable for uneven intervals. So first we will go through by algorithm. Okay. So here algorithm starts. We will take the input number of data points n, array x and y, and the interpolation value xp, which is 9. In the question it is given f9. So interpolation value will be xp9. Now we will start the processing. Initialize sum equals to 0. Now start a for loop for I from 0 to n minus 1. Initialize a temporary product p equals to 1. And for j from 0 to n minus 1, if I is not equals to j, if you have go through my Lagrange interpolation video, you will be understanding how the processing and algorithm program have been written here. So if I is not equals to j, update p. P equals to p into xp minus x of j, x of I minus x of j. This is a main Lagrange concept we are using here. Now add to the total sum. Sum equals to sum plus p into yi. Now we will output the interpolated sum. Here we will write the program. You can see, you will understand better in the program. Here we will take array x and y, and value to be interpolated xp equals to 9 and yp equals to 0. For I in range len of x, which is length of x, p equals to 1. For j in range length of x, uh, uh, if I is not equals to j, then we perform the calculation we have written in our algorithm, like p equals to p into xp minus xj divided by xi minus xj, and yp equals to yp plus p multiplied by yi, and print the interpolated value at x. Now we will solve the question with numerical evaluation and using our algorithm. So we will calculate the multipliers L0, L1, L2, L3, L4 for x equals to 9. Here you can see, first we will calculate L0 9. So here 9 minus 7, 9 minus 11, 9 minus 13 and 9 minus 17. These all are the values given in the question, except the zeroth value. If you can see the question, yeah. Here 7, 11, 13 and 17 is used in the F0, but 5 is not used, and in denominator we will see all the other elements are get subtracted from 5. So this is a basic Lagrange's concept which we have followed here, and we will calculate the the L09, which is 0.111. Now for L1, here you can see 7 is gone from here and 5 came in. Now we will subtract, now 9 is subtracted from all the elements except the 7, and you will see, you will be seeing that all the elements in denominator get subtracted from 7. So this is how we calculate L1 9, which is 0.533. Similarly, we will calculate L2, L3 and L4 and takes the value. Now L49 is calculated. Now for the final answer f of 9, we will and we will multiply them with their function values. Like for f of 9, it is L0. And if you will, I will show you the question first. You will get to understand now. For 5, its function value is 150. For 7, it's 392. You can see here for 5, here we will multiply by the function value of 5, here multiply by function value of 7, and similarly in other elements. After adding them all, we will get the final answer of F9, which is 843.33. Now we come to the complexity. The time complexity is order of n square due to nested loops. The space complexity is order of n to store the arrays. And geometrical graph interpretation says that Lagranges find a smooth single polynomial curve that passes perfectly through every single data point, providing provided allowing us to guess the value in between. Now here we come to the question number 3. Uh, it is if we you have go through the internal videos, it is the same question which we have solved in the our interpol our internal video. So we will not doing that whole, but we will go through that just to revise you all. So if you can see, we have to find the function 2.5 and 3.5. So find bounding, we will write the all functions f23, f33, f24, f34. These are the functions which are related to this and this value. So we will write them all and interpolate them horizontally. So we will first find f2.5 comma 3, f2.5 comma 4. So 2.5 comma 3 is coming between f2 comma 3 to f3 comma 3. So we will take these two values and divide them by 2 and take their average. And similarly for f 2.5 comma 4, we will take these two values and divide them by 2 and we will get the average value. Now interpolate them vertically. So if you see f 2.5 and 3.5, so you will assume that 3.5 is coming between 3 and 4 and it is same. So we will take these two inputs and divide them by 2 and get our final interpolated value. For other many things, you will go to my internal videos. Here I have solved this question in very detail and in very explanatory way. Now we come to question 4, where what question 4 is says. We will go through the question 4. Here is the question 4. Obtain general quadrature formula using one from the following. It's a Newton force or quadrature, and obtain Vidal's rule, derivation, algorithm, program, time space complexity is into that. So we will Vidal's rule is a highly accurate way to find the area under the curve, which is the integration. It is derived from the Newton's code formula by setting the number of intervals n equals to 6. We will be doing this by using Newton's code formula. Okay, so now go through the first derivation step by substituting n equals to 6 into general Newton quadrature formula. Integrating, ignoring higher order differences, we obtain the coefficient weights 1, 5, 1, 6, 1, 5, 1. So, which is the how to find this. Now we will come to the algorithm. Algorithm, we know the formula. What's for Vidal's rule? It's I equals to 3h by 10 and y0, and we will implement these weights here. So 1, so y0 into 1, and 5, y1 into 5, 1, y2 into 1, then 6, so y3 multiplied by 6, and then also again 1, y4 multiplied by 1, then 5 and 1 similarly. Input here lower limit alpha and upper limit beta, and number of interval n must be multiplied of 6, multiple of 6. So processing. Here the processing work come. We calculate the step size h by subtracting b minus a by n, and now compute all y values for each x step and apply the weights in repeating loop to the sum, the y values, multiply the total by 3h by 10 and the integrated area is calculated. So we first define the function f with the argument x and which return the value of our given function which has been given to us, or we are taking it as an example function. Now we will define the Vidal's rule function, which takes a and b as argument. Where n equals to 6, it is minimum intervals for Vidal's. We know that the Vidal's rule is obtained by putting n equals to 6 or multiple of 6. So now we calculate h by subtracting b minus a by n, and y equals to f a plus I into h for I in range n plus 1. Here we are calculating the value of h. Now to find the final integral, we will uh, we will write these formula, which we have written in our algorithm. We have wrote this formula here. So here 3 into h by 10. So it is outside, and then it is multiplied by y0 plus 5 into y1 plus y2 plus 6 into y3 plus y4 plus 5 into y5, and then into the uh, y6. Here it is misprinted. Now, so this is the formula, and we will return the integer. And then we will write the main program calling function and Vidal's rule. Okay, that's all. Now, time complexity. Time complexity for this is order of n, where n is the number of intervals, and space complexity is also in order of n to store the y values. Now we solve the next question, which is the fifth question. We will go after the question. To solve the system using any one method. So here three questions is given to us, and there are option of three methods: Gauss elimination, Jacobian, Gauss seidel. And we have to write algorithm, program, interval, test solution, uh, or time and space complexity for that method. We have chosen. So here we have chosen the Gauss elimination with pivoting. We will solve video with three equation using Gauss elimination pivoting. This meaning we rearrange the rows so that the large number is always at the top left, which prevents computer from dividing by tiny numbers and making errors. Now, three equations given to us are these. In step one, we will swap the rows. As you can see, you all know that the larger whichever row has first larger first element, it can be the first row. So we will swap the row 2 and 1. So here are it. We will swap the R1, R2, and R3. Now we will eliminate X from R2 and R3. If you see R2 is equal to R2 minus 1 by 3 R1. You all are curious how 1 by 3 is came. So 1 by 3 came here like coefficient of x in R2, which is 1, and in denominator coefficient of x in R1, which is 3. So it's R1, and in return, by applying that, we will get 0x, 1.63y, 2.66x, and 10.66 as our equator value. Now, so we will do the same for R3. Here you can see that how to can it is the coefficient of x in R3, and 3 is the coefficient of x in R1 multiplied by R1. By doing this in R3, we will get R3 as 0x, 1.66y, 1.33 is z, and is equals to 7.33. Now we element by y from R3. We will again perform the pivot again if needed. 1.66 is, you will see that 1.66 is greater than 1.33, so we will swap R2 and R3 to be safe, then eliminate. Now we solving the upper triangular matrix, give exact integer answer, throw back to the substitution. Now 1 plus 2, 2 plus 3, 3. Here by substituting, as you can see, here these two get 0. By performing eliminating y from R3, like we will eliminate this term from I3 by performing this operation with R3 by using R2. So we directly able to equate, like it will come like 1.33 z equals to 7.33. So it will come in like this structure. So we will equate them and get the value of z. So solving the upper triangular matrix, it will give us the exact answer for vector substitution. So we will get the answers as x equals to 1, y equals to 2, and z equals to 3. And now applying these values in the equations to test the solution, and we apply this and it's came 14. So you can see that, yeah, it matches perfectly with the 14, then 10, and then 14. So now equation 2 is coming 10. So both the equation got matched. So now the complexity for this is the time is in order of n cube for elimination, and the space is order of n square for the matrix. Now, next question, we will solve the seventh question. Here, solve ordinary differential equation dy by dx equals to x plus y, comma y0 equals to 1, and find 0 0.5 and y1 using any one of the following method. And write algorithm program, iterative solution, time complexity for that. Yeah. Here it is. So this is the function x plus y given to us. Now y01. So the x0 value will be y and y0 value will be 1. What we have to find? 0 0.5 and y1. Okay, now we will go to, so you can see by seeing these three, we will guess that h would be 0 0.5. Now we will go to that. We will solving it by using the Rumde-Gupta method of fourth order, which is also known as the RK4 method. So now RK4 is the gold standard for the solving differential equation. It's take four different sample slopes K1, K2, K3, K4 across a single step and averages them out to make highly accurate prediction. So firstly, dy dx equals to x plus y given to us. Also, y0 equals to 1 also given, and step size h equals to zero point 0.5, which I have told you earlier. We'll guess it. Now we are finding y 0.5. So firstly, you can see what K1 formula says. It says h multiplied function x0 comma y0, which gives us 0 0.5, which is x value, and x0 and y0. So we will sum that as you know what are the function. So we will get zero point 0.5. Now for K2, we will also apply the Kutta method, the formula, which is h into function of x0 plus h by 2, comma y0 plus k1 by 2. See students, these are the important or the point where most people make the mistakes. Here, this is our first value which will go to the function, and this is the second value which will go to the function. Okay, so we will by doing that and putting values, zero point 0.5 is h value and 0.25 is x0 plus h by 2, and 1.25 is the y0 plus k1 by 2, and we will add them and get the value of K2, which is 0.75. Similarly, for K3 here, K1 changes to K2 and we use the K2 instead of K1, and by doing similar, we will get another value of 0.8125. Now for K4 also apply the formula and use the value of K3, and so solving that we will got the value of K4, which is 1.15625. Okay. Now we will, the final formula is which says y 0.5 is equals to y0 plus 1 by 6 y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. So now we will put these values into the formula, and get the value of y 0.5 equals to 1.7968. Now repeat, now for y1 you will do that at your home and comment the answers. Okay, so repeat exact same k calculations, but use x0 equals to 0 0.5 and y0 equals to 1.798, as we have to choose y the x and y values just previous, just like we are finding y1, so we have to choose the value of y 0.5 and x 0.5. So remember this in mind and solve the y1 and tell me the answers. Okay. So the final computational yield of y1 is will be your answer will be coming nearly about 3.436. Okay. Now complexity for this is in order of n. Here n is the number of steps and space complexity is in order of 1. Okay. Now here our last question came. Question number 8. We'll see what the question says. Okay. Here the question says explain convergence order theorem. Prove that order of convergence of secant method is less than 2. What L conditioned equations explain successive refinement procedures for solving them. And the third point is prove that the sum of Lagrange's coefficient is unit. Okay, so there are three parts in the eighth question. We will solving them one by one. Okay, so first in the order of convergence. Okay, so the convergence order theorem dictates how quickly an error decreases. Means how efficiently, how fastly the error is decreasing, and the order of convergence, which is denoted by P for the secant method, is defined by the Fibonacci-like recurrence relation of its errors. Solving the characteristic equation P square minus P minus 1 equals to 0, it yields P equals to 1 plus root 5 by 2, nearly equals to 1.618. Because 1.618 is less than 2, its convergence order is strictly less than Newton Raphson, which is exactly 2. So now for the second part, we will go what are the ill conditions equation and successive refinement. So ill conditioned equations are these are the systems where a microscopic change in the input, like rounding off a decimal from 0.005 to 0.006, causes a massive and chaotic change in the final answer. This system is extremely sensitive. Okay, like we have done these type of methods in our internal first question paper, where we have understand what are the changes between the cases. We have changed the value just by a little bit and interchange the equations. So yeah, you can go through that and learn from that. Okay, now what is success in refinement? This is a rescue procedure after solving a rescue procedure. Successive refinement is just like you are in the middle of something and you need a rescue. So it is a rescue procedure. Just like after solving a matrix and getting an approximate answer, we calculate the residual error. When we then solve the matrix again using the error as a new target to find the correction factor. We add this correction back to our original answer to refine it. That's how you are getting an answer. Now you are getting an answer. Now you will check the error, then calculate the residual error, then solve the matrix again using the error as the new target and find the correction factor and add this to our original answer to refine it. Also, you will remember in the Euler's method, there is also a correction formula which comes in a Euler modified theorem. Okay. Now, third part of the question and last part of our exam paper is the sum of prove that sum of Lagrange's coefficient is equal to unity. Now, to prove that the sum of Lagrange's coefficient, which is summation of Lix is equals to 1, we can interpolate the constant function f of x equals to 1 according to the Lagrange formula, which is px equals to summation Lix into fxi. Since fxi equals to 1 for all points, px equals to summation of lix into 1, because a polynomial of degree n that passes through points where y is always 1 must be the flat line. So px equals to 1, it is perfectly proves that summation of lix equals to 1. Thank you. That's all. We have solved all the questions of our final and some examination of numerical analysis and design. Okay. Thank you for watching. Please like, share, and subscribe. Thank you. Have a nice day to you all.